Hello. So I think I'm now live, ready for this GCSE live stream. This is going to be about half an hour of GCSE physics, all aimed at paper 1, which is coming up in just a few days' time. And then from 8 o'clock onwards, I'm going to be doing A-level preparation again for kind of physics paper 1. So I hope everybody out there is doing all right. I'm a bit red. I've had sort of like a bit too much time in the sun maybe, but I hope everybody out there is doing okay. And I hope that, I suppose a lot of you GCSE people are going to be preparing for English literature tomorrow. But I guess by now you probably know the text, you know some quotes. So yeah, hello Evil, hello Joe Smith, hello lots of people in the chat who are kind of joining me at the moment. Tonight the plan is we're going to start with some, again, kind of paper 1 questions. I've got some Lego. So this one here will be opened at about 8 o'clock, I think. Trying to see what we can add to our collection. So we've got various kind of sort of space people, aliens and so on. And hopefully we're kind of going to aim for that green-headed man tonight. But we'll see. We'll see what happens as we open this Lego later in the stream. Right, so somebody says, I don't know if you've noticed this, your playlist on equation sheets has a Try Not to Laugh compilation. No, Joe Smith. Okay, can you send me a link to that? I'd love to see that. My playlist on equation sheets. Okay, right. I'd love to see that. I've no idea what that would actually be like. But yeah, Joe, send me a link to that if you can somewhere. It would be great to see that. Maybe not now, but definitely at some point. And also, if anybody out there is kind of just watching this stream for the first time, I'm going to be going through some questions. These questions actually come from my practice papers. You can buy these in the Physics Online shop on Shopify. So that's physicsonline.shop, and that means you can download your own set of papers for you to have a go at. There are 12 papers in total. I've got 6 sets of paper 1s and 6 sets of paper 2, all aimed at GCSE triple physics. So yeah, right, let's just start some questions, shall we? So this one here, figure 1, shows a wind turbine. It's used to produce electricity for houses all over the country. Choose a correct answer from the box to complete each sentence. So the wind turbine blades turn something which is connected to a generator. Now really, this is the question about all ways that we generate electricity. Basically what we have is we have something which we use to generate electricity. That's a generator. Okay, and that's basically the thing that you learn more about in kind of sort of for the second thing where we're looking at this link between electricity and magnetism. So a generator has to be turned, and that's going to produce electricity. Now, in order to turn that, we need some kind of turbine. Okay, so the turbine is connected to the generator, and this needs to be rotating. And there are many ways we can do this. Basically, we just need something turning. So what we could use is we could use water. For example, we might have water going past, maybe through a tidal barrage. We've just got actual water going past, causing the turbine to spin. We could have steam causing that to spin, and that's what we have in lots of power stations. So, for example, in coal, oil and gas, and also in nuclear fission, what we're doing is we have hot things which we burn, which can then cause water to turn to steam, and that causes the turbine to turn, or we can just use the wind directly. Okay, so the wind turbine blades, they turn a turbine, and this turbine is connected to a generator. So as we have this generator turning, something is used to change the potential difference for transmission along power lines. Now, what we want to do is, and this is again something that you cover in a bit more detail in paper 2, where we're actually looking at how transformers are actually made and constructed if you're doing triple science. So this is basically something that we can use to transform the potential difference to a higher potential difference, and therefore a lower current to reduce energy losses. And we use this, we do this with a transformer. Okay, transformer, James Stevenson was correct for the second answer, well done. I'm not going to be necessarily discussing content for Unit 3 IAL Physics at the moment. says Mina. Basically, I'm going to be doing more stuff aimed at the kind of paper one topics for GCSE for the next half an hour. I think it sort of says down there. And then from 8 o'clock, it's more A-level paper one topics. But hopefully that's going to be helpful for some people. By the way, in the chat at the moment, do let me know which exam board you take. If you are AQA, Edexcel, OCR, Edexcel International, maybe CIE, do let me know. Okay, Habs, is this GCSE? Yes, it is, yeah. Basically until 8 o'clock, it's going to be GCSE. AQA, says Habs. James, AQA. Hyperslane, like that name. Yeah, AQA as well. So it seems like most people tonight are AQA people. Okay, right. Why is it unlikely that a wind turbine would produce a constant output throughout the day? So the reason that we don't get this consistent output like we would if we had maybe a fission power station, because we can control the rate of nuclear fission. We can control the rate at which oil is burnt, or coal is burnt, or gas is burnt, and they're things which are controlled. Whereas when we have these renewable energy resources, it's basically Mother Nature. And therefore, basically the wind speed changes. Throughout the day. And therefore, if the wind speed is going to change, it's going to change the force actually on the turbine blades so they spin at a different speed. James is doing AQA, Evil is AQA, Edexcel for Hammered Gaming. Habs, will it go over most of the energy topic on physics? Not necessarily tonight. I'll be just kind of covering some exam style questions. Let me just see if I need to adjust the camera. But if you want to revise the whole of GCSE physics, I do have videos over at GCSE Physics Online. Okay, Heads says you do OCR A-level. Do you know what? OCR A-level, it's a good one. It's all fine. Okay. But yeah, Habs, if you want to revise anything in particular, you can find videos about everything. And this is for everybody else watching. If you want like a summary video where I cover the whole of AQA or any kind of GCSE physics, you can just look on YouTube. You can look down my kind of video playlist and you'll find lots and lots of GCSE videos there, but you can also find everything on my GCSE Physics Online website. Okay, right, so there we go, not too bad as we start that. Okay, we then have some data. We've got a couple of charts here. We've got the percentage share of electricity generation over these years. We've got the percentage for solar, and we can see this goes up to about 5%, whereas wind power has a different scale on the y-axis. We go from sort of 5 up to about 25, and you can almost see that here, the kind of trend, it's kind of like that, and the trend here is more like that. Okay, so we've got a different shape trend, even though both of them are kind of increasing. Right. Describe one similarity and one difference between how the share of electricity generation for solar and wind has changed over the period 2012 to 2020. So what we're going to look at is both of these sets of data. We can see for both of them they've increased. What's the similarity? What's the difference? So I would say that things that are similar are that the percentage share of solar and the percentage share of wind has increased over that time. Sorry, I'm just looking forward to my answers. Excuse me. Sorry, just gonna. So the similarity is we could say that every year they increase. Now, this is something that you don't have to know before the exam. This question is very much about the interpretation of some data that they've given you. So all of you, thank you, Joe, for the bless you. So all of you will be given questions with data that you've never seen before, and you won't have seen in any past paper questions. You won't have been shown any of this in any lessons that you might have had in school. But it's a case of just looking at the data and interpreting it to see what it actually means. So the difference, though, I would say that we could look at maybe that the percentages are quite different. So that's up to about 5%. That's up to maybe some 5 to 25. So much bigger percentages here. But I would say if we were to sort of continue this line along, we'd see that actually this kind of line is kind of leveling off, whereas this one seems to be going up and up and up. So we could say that wind power maybe increases its percentage share in later years, whereas this one doesn't in terms of the rate of increase. So we could say that maybe the rate of increase of wind increases in recent years. Okay, and the word rate, it just means with respect to time. Okay, okay, we've now got a question. I want all of you to have a go at this. So we've got a solar panel produces a mean current of 3 amps over a 24-hour period. Calculate the total charge transferred from the photovoltaic panel. So often these solar panels are called PV cells or PV panels to be photovoltaic. The word photo just means to do with light, and the word voltaic is really to do with electricity. So we're talking about we can generate electricity from light, and we're going to look at a whole day. So I would say the first thing for something like this is you need to write down an equation. Now all of you will be given a data sheet for your GCSE exams, which means to some extent it's not really an advantage having these kind of questions because most people will be able to do them. And therefore, if you wanted to go for the high marks, you need to get the kind of other marks in different places around the exam. So a lot of people are going to get 100% on all of the calculations, and therefore you need to make sure that you can write your explanations clearly in order to kind of get to those really, really high grades. So Evol, yeah, I think your keyboard is broken. You should have put Q equals IT. We always use capital Q for charge, capital I for current. And the total charge is going to be equal to the current, which is 3.0 amps. And we're going to multiply that by the time. But of course, the time is going to be 24 hours times 60 minutes times 60 seconds. So we've always got to convert our time into seconds, and that's our standard unit. So if I just do this on a calculator, we've got 3 times 24 times 60 times 60, which is equal to 259,200. Okay, and yeah, Hyperslade, yeah, I think you got a massive number, but that's fine. James Stevenson, yeah, you got the right thing. So the unit is, because it's our charge, it's measured in coulombs, which is C. And I think that Joe Smith has got a perfect answer. So he's written out in the comments in the kind of live chat, Q equals IT. We've got the time converted to seconds. We've got 3 times that. He's given the answer as 259,200. But then what's really good is he's actually given the answer as 260,000. Now that's not necessarily, and of course standard form would be fine as well. So 2.6 times 10 to the 1, 2, 3, 4, 5 times 10 to the 5 would also be perfectly good. Now at GCSE, you will get the mark for writing this down, unless it tells you to write to an appropriate number of significant figures. I would say for this, we've been given 2 significant figures in the raw data, so we know that's about 3.0 amps, and therefore this answer over here, 260,000 or 2.6 times 10 to the 5, is also kind of 2 significant figures, we think. But, you know, this is the best way. This is like the kind of gold standard that you want to get to. How is that 4 marks though? 1 mark for writing out the equation, 1 mark for doing the working, 1 mark for the right number, and 1 mark for the units. So that's basically a way that you can get 4 marks for a question like this. Okay, standard things you're going to be doing all the time. Okay, we then have a different solar panel. Now this question here, forget it's on a GCSE physics science paper. Okay, all of you are doing GCSE maths. And I would say that everybody here, you've already done paper 1 for GCSE. I would say the level of maths is like up here, and the level of like science is kind of down here. So a lot of you have all the math skills necessary, and that means sometimes there's going to be questions in your science papers which just take your GCSE math skills to answer. So for this one, a different solar panel has a power of 700 watts for each square metre. Calculate the area of panels that will be required to provide an overall output of 53 kilowatts, giving your answer to 2 significant figures. So the first thing we might say is that 53 kilowatts is the same as 53,000 watts. Okay, so first of all, we've identified that there's maybe a prefix here. We know what that means. So a kilo is 1,000. We then know that that's the total power, but each of the panels provides 700. So if we look at the total and we divide that by the energy for each thing, that's going to be 53,000 divided by 700, which is equal to 75.714. Now we want to know the area, and we want to give this to two significant figures. So it's basically taking this number here and giving that to two significant figures. And if we do that, well, 75.7 is going to be equal to 76 square meters. So yeah, hyperslane 53,000 over 700, approximately 76 square meters. James, you're asking about, would it be better to give this answer in standard form? I would say it doesn't matter. At GCSE, it doesn't matter. Just write down the number. You'll get all the marks. Even at A-level, that's fine. But I would say that this is better, but you don't have to do it. But if you do give your answers in standard form, then it does show that you've given your answer to an appropriate number of significant figures. So I would say, in terms of pure physics, that's correct. That's the best way to give it. But you will always get given the marks by giving your answer like this or like this. What topics am I going to cover? So I've just done a couple of questions here to do with electricity and like power generation. But you can see that this question was about different forms or different ways in which we can generate electricity. So that's kind of that topic to do with energy resources. And then there's some questions about electricity. And then there's like a mathematical skills one. Okay, the next question we're going to do is again about electricity. We're just going to look at some IV graphs, which I've done a lot. And if anybody's watching this stream and they haven't seen it before, then you can obviously go back to my GCSE website. There's a link in sort of beneath this video on YouTube, and it's like my gcsephysicsonline.com/live. If you go there, you can see all of my previous streams and you can see the topics for every single one. Okay. We've got an IV characteristic of a component. Identify the component, circle a correct answer. This is a question which will take you 5 seconds. Habs has already said filament lamp. What Habs says James. So a filament lamp has this thing over here. So we've got current on the y-axis, potential difference on the x-axis, and that's why it's called the IV characteristics, the current voltage characteristic of a component. You might remember that a resistor looks like this. A diode looks like this. A filament lamp, as we've seen above, has this kind of S shape or an F shape. And a thermistor, you don't need to know that. But in actual fact, if you wanted to look at a thermistor, it's actually a shape like that. Okay, but that's not something you need. This is kind of like the opposite to a filament lamp. Okay, complete the circuit below to show what would enable the graph up here to be produced. So this is our component, and what we need to do is add the component things. Now this is a component. What we want to do is we need to add these things: a variable resistor, ammeter, voltmeter, open switch, using the correct symbol for each. Now it doesn't really matter which order they go in, apart from we have to have an ammeter in series with the component. We need a variable resistor, which we can use to change the current in that circuit and also the share of the potential difference across this. And also we need this kind of open switch. Okay, and basically then, and you don't really even have to use a ruler, to be honest, but the thing is that you have to make sure is that there are no gaps in that circuit. So this is like my rough thing I've done as I'm talking. You can see there's no gaps, and that means we have a complete circuit, apart from obviously there's an open switch. And we've got the ammeter in series with the variable resistor in series with the open switch. And the thing that we have in parallel is going to be the voltmeter. Okay, now that would get us 4 marks. We've got the ammeter, variable resistor, open switch in series, the voltmeter in parallel, and we've got no breaks in the circuit. And yeah, okay, somebody has a doubt. G, Dominator's official. Hello again, I know you've been in the chat before. What's your doubt? Yeah, and basically, James, This is the IV characteristics practical. That's all we've got down there. Right, Raven, I will give you some tips in about 10 minutes time if that's all right for Edexcel IAL. But to be honest, by now you've done many years of study and I know that. So if you have your Unit 3 IAL exam tomorrow, you're going to be fine. I know that you are because you've been watching my videos. I know that. And therefore you're going to be good. Okay, I would say that the last thing to do is just make sure that you just kind of look over any kind of notes that you have on the night before your exam so you're happy with those. Don't necessarily start some big project and lots more past paper questions you've never seen beforehand. Get a good night's sleep and just go into it knowing that there will be some tricky questions, but most of it is going to be absolutely fine. Okay, right. Is this part of the whole paper revision as well? Yeah, this is kind of revision, spirits, yeah. I reckon this is kind of revision because I'm just talking through the kind of questions that could come up in your exam next, is it Wednesday? Yeah, so you've got a couple of days and I'll be here tomorrow night and the night after. Okay, so the next question, and by the way, if you want to buy these like practice papers that I've made, they all come with a full set of work solutions as well. So you can see, in addition to the mark scheme and the questions that I've written and made for you, which you can't find anywhere else, there's also a full set of work solutions. And there's videos where I explain everything as well, because that's what I do. I just love making videos. Okay, so 3.3. What should be a safety precaution taken? So if you're doing the IV characteristic, close the power supply quickly and take readings to avoid the wire overheating, burning. Hyperstain, perfect. So don't leave the switch closed, Joe. Yeah, so basically you could say something along the lines of only close the switch when taking readings to stop it overheating. And when you're doing the IV characteristic, you want to make sure that you keep that switch closed for a very short amount of time. G Dominators official, I'm afraid I don't have any specific recommendations for the IFO. Okay, so I think it's just a case of doing as many British Physics Olympiad questions as possible. Okay, the student takes some readings for a different component. They measure the current as 0.30 plus or minus 0.1 and the potential difference is 2 plus or minus 0.05. Calculate the maximal possible resistance of the component with these values. So I would say for this, we know that there's an equation that says V equals I times R, and that means the resistance is going to be equal to the potential difference divided by the current. And basically to get the maximum possible value of R, we want to have the maximum possible value of V, and we want to divide by the smallest number possible. So again, that's kind of like a math skills kind of question. So we want to have the I min. Now the maximum possible value for the voltage, well if it's 2 plus or minus 0.05, that's going to be equal to 2.05. So that's the upper kind of possible value that we could have. Okay, and so we've got like the upper bound of Vmax and the minimum bound or the lower bound of I. That's going to be 0.3 plus or minus 0.01. So that's going to be 0.29. Okay, so that should be the maximum divided by the minimum will give us the maximum value for this. So this question here is actually just a maths question. And this gives an answer equal to 7.068965517. Now the resistance I would give to maybe 3 significant figures, or no, maybe 2 significant figures, because that's kind of 2 significant figures there. So this would be equal to maybe about 7.1 ohms. Now, I suppose the minimum value would be equal to 1.95 divided by 0.31, which would be equal to 6.3. So there's quite a difference where the maximum is 7.1, the minimum is 6.3, and that's just with these very, very small differences in resolutions. Okay, hopefully that's all good. The student performed the same experiment again with the same type of component, but with a higher resistance. Sketch on figure 3 the results you'd expect to get. So what we need to do, and I think this is a question that I've not seen actually come up in a GCSE paper yet, but if this comes up and you've bought my practice papers and you are doing and actually watching this stream at the moment, then maybe this is kind of your advantage. So what we need to have is something with a higher resistance. Now again, we know that V is equal to I times R, or R is equal to V over I. Okay, now if you had the same component with a bigger resistance, or actually I'm going to say I is also equal to V over R. Okay, so imagine you had the same value of potential difference. If you had a bigger value of resistance, it would make I lower. So maybe rather than having this current, we'd have a slightly smaller current. And again, we have a bigger potential difference with a bigger value of resistance. As R increases, this is going to make I smaller. So that means we'd always have a smaller value of current. And if we plotted it on the graph, we'd get something that looks like this. So we have the same shaped curve, but everything's a little bit lower down. And equally, it would be kind of above that line. Sorry, that should go more around here. Ignore that. Okay, and therefore we'd have a curve that looks a bit like this. Okay, and there we go. I reckon that is the end of the kind of stuff tonight. Now, I will be doing lots more revision ready for GCSE. Of course, if you want to find anything to help you, I do have hundreds and hundreds and hundreds of videos over at GCSEphysicsonline.com. I've got loads as well on this YouTube channel on Physics Online, my massive YouTube channel. There's also some videos there where I do like summaries of different bits and pieces, and I reckon that you could basically get a grade 9 using the resources that I've made. Okay, I've got a couple of minutes. Does anybody have any GCSE specific quick questions I can help with before we go on to the unveiling of the Lego box and the minifigure inside and the kind of A-level part of the stream? If anybody has any questions, put them in the chat and I'll do my best to answer them. I can't promise I answer everything because I know there's like a lot of people watching, but I'll see what I can do, especially if it's like an easy answer. Okay, right. So there's a bit of a time delay between me talking, you hearing this, and then actually getting the kind of things in. So, anybody got any questions I can help with? Okay. Not at the moment. Okay. Can you revise English Lit Paper 2 GCSE? I'm afraid English literature is well beyond my comfort level. I would say when I did my GCSEs, I got, this is in the olden days, I got like A stars, before they had like grade 9s and stuff. Maths and science, so that was all good. My two lowest marks were English language and German. I just didn't like, I just wasn't very good at English. It just didn't come naturally to me. Okay, right, so would question 3.4 be a question that could appear in the exam? So I reckon, yes, it could. I reckon all the questions I've written could potentially come up. They are all within the bounds of the specification and they could ask that question, but it would be tricky and potentially it would cause lots of people to complain, but there's nothing there about the skills that you have. It's maybe unlikely it would come up, but it's definitely the kind of thing that would kind of it would sort out the grade 9 students from the grade 8 students. So yes, potentially it could come up. My favourite Greek letter, currently it's Zeta. I don't think it's used enough. So yeah, Zeta is my favourite Greek letter at the moment. Should you watch the A-level part of the GCSE student? If you want to do physics next year, okay, first of all, I'd say you don't need to I mean, if you want to, you're more than welcome. I'd love to have you along to see what's going on. But I would say if you are a GCSE student who's going to be doing A-level physics, buy the Daily Workout Book 1. You can find this on Amazon, and it's got questions that start at the beginning of July, and there's questions all the way through the summer holidays, and then it goes into questions in September, October, and so on. And if you do these questions, you will be much more prepared for A-level physics. I guarantee this book will help you enormously. Okay. Do you have to talk about how energy is used to break intermolecular bonds during specific latent heat within an exam question? Yes, I think you should, because that you can then mean that, I suppose, then shows that the energy transferred to that substance is increasing the potential energy of those molecules, but without increasing the kinetic energy stored, and that's why the temperature stays the same. Hopefully that helps. Somebody's got another question. If you have a household wire connected to the national grid, what happens to the electrons? Do they flow back or remain stationary if the switch is closed? So the electrons, all they do is they just go back and forwards because it's an AC supply. The electrons, if the switch is closed, then you've got a bit of a kind of complete circuit, and the electrons are just going to go back and forwards. Hopefully that helps. Right, should we do some Lego? I want to do this. So this is the latest set of Lego for part of my minifigures series. We've got quite a few already. We've been collecting well. I've ticked off the ones I've got. You can see there's quite a few I haven't got yet, including like the kind of whatever that purple thing is. That one there, the space baby, but we'll see what we get tonight. So we've got a few already. So let me just zoom in on this. Okay, and what we'll do is maybe just release a bit at a time. Okay, right, so for this one, let's see, there's a bit of a... Okay, so we've got the packet. We have a green head. Okay. Oh my god, this one is good. So we've got... Do you know what? That has to be my favourite minifigure torso. Oh, that's by the way, that's pen on me, not like some weird rash or something. Okay, so we've got like a shooting star there. And on the back, we've even got, I don't know how much I can zoom in with my camera, but we do have the Earth in space and the moon as well. Look at that, we've got the Earth and the moon. By the way, that is so... I mean, that is like just a misconception that it's just spreading that the moon is actually really close to the Earth. Or maybe it's taken with a bit of perspective and actually that's the moon's a lot closer than the Earth. Anyway, so we've got the torso there. We then have this spaceship thing here. And we've got somebody with some face paint on. That is an awesome, awesome figure. That goes on the top there. So they're like the kind of alien spaceship. Over the Earth, and then we've got again the best base plate ever with the stars on. So I reckon that is probably one of my favourite minifigures. Let me know what you think. Best minifigure ever? I reckon it's definitely up there. So look at that. I need to get some more of these. If I could just have 100 of these, I'll be incredibly happy. So we've now ticked off yet another spaceman or space person, an alien figure on our journey. Yeah, there we go. Right, so not too bad tonight. We've got another person added to the collection. Okay, should we get on with some A-level stuff? Now it's after 8 o'clock. So for all of you doing A-level physics, don't forget, if you want to have guaranteed success, not only in your exams, but in later life as well, then you can buy stuff over A-level physics online, including, of course, my practice papers, ideal for the kind of practical skills. But what I'm going to be doing now, and actually I'm going to be doing this for the rest of the week, and this week and next week, is I'm going to be doing some OCR questions, but the questions are going to be relevant for students doing Edexcel, International A-Level, WJEC if you're in Wales, did I say Edexcel, AQA, basically anybody doing physics. Now the reason I'm doing OCR papers is because I'm not allowed to show AQA real papers on YouTube. I can't do Edexcel things in case of copyright strikes. OCR are all happy with this. So the only reason I'm doing OCR and not another exam board is because of copyright, and that's just a YouTube thing. Because I don't want to have my channel taken down. Okay, so, sorry, let me just go down in the chat. It's just gone a bit weird for a sec. Okay, right. Yeah, okay, so how come I don't do combined science AQA papers, Meshraf? Yeah, the papers I've got are suitable for combined science, but I just thought I'd cover the whole topic this year. And then if you're doing combined, it just means that when you do the practice papers I've written, you just need to take out the questions which aren't suitable for you. Okay, right. Okay, so these questions here are from May 2022. Obviously, I'd like all of you to play along at home, if you talk about playing. So, do I suggest doing multiple choice at the beginning? Yes, I do. I reckon if the multiple choice in section A, just do them. But I would say the thing which is really important is spend 30 minutes on this section, a maximum, and then move on. If you can't get the question straight away, leave it and come back to it later. Okay, so let's have a look at the first question. So we've got possible scalar and vector quantities. So which of these are scalar? Well, I would say looking down this list, what colour shall I use? I'm going to use purple. Acceleration is a vector, so that's not correct. Displacement is a vector. Frequency and mass are both scalars. And if we think about vectors, well, amplitude is just the maximum thing, so that's not one of them. Wavelength isn't one of them, but momentum is a vector, and so centripetal force. So the only column which is correct is D. So Josh, Vapor, Matthew, that's good. All getting the right answer straight away. So for the first one, the answer is D. And my approach to this was basically to look across these, and you can always use a pencil in the exam to kind of like get rid of the ones which you know are incorrect, because a pencil isn't as final as a pen. So yeah, has Zed Physics done these already? Of course he has. I'm sure he has. Anyway, I'm bringing the Physics Online take on these to what Zed Physics has already done. Okay. Okay, the diameter of a wire is measured in 5 different places along its length. Here are the results. What is the absolute uncertainty in the diameter? So is it A, B, C, or D? Now, in order to work out the absolute uncertainty, we need to think about the fact that we've got multiple things here, and therefore it's going to be equal to half the range. So half the range is equal to the absolute uncertainty when we have repeated readings. Now the biggest value is 1.92, the smallest is 1.86, and that's equal to 0.06. So that's going to be equal to our range. Now half the range is going to be equal to 0.06 divided by 2, which is 0.03. And therefore the answer here, as let's see who's got the right answer, we've got Miss Katie Bell, hello, Toby, Badger, Maddie, Anch, excellent. Sinzoku, yeah, so the answer for this is B. So when you have repeated readings, the absolute uncertainty is equal to half the range. If you had a single reading, so say for example, we had a single reading that was equal to 1.92, in that case your absolute uncertainty would be the resolution, which in this case would be plus or minus 0.01. Okay, so if you had a single reading, it would be 0.01, but because we have repeated readings, it's going to be B. Okay, now again, as a lot of people, I want to sort of try and make clear, although this is the question on paper 1 for OCR, this is not necessarily completely suitable for everybody, because some people might be asked some of these questions on paper 2 or paper 3. However, all of your exams are in the next kind of 3 or 4 weeks, so this is all good revision whichever exam board you're doing. But the only reason I'm doing OCR questions is because of copyright issues for showing AQA ones. And actually, yeah, AQA paper 1 or paper 3 could have this. Mashraf, thank you so much. I'm the GOAT. Yeah, and also this is, yeah, I mean, I think uncertainty could come up on every single paper. I'm not going to do the whole paper, Luca. I'm just going to do the multiple choice questions as part of the stream. Okay, so the next one. A student has plotted the velocity against time graph for a trolley moving down a ramp. Which of the following pair of quantities can be determined from the gradient and the area? So what we'd have is a velocity time graph. And if it's something which is accelerating down a ramp, it would either be a straight line if we had no friction, or if we had a bit of friction, in reality, we might get something a bit more like this. Okay, everybody's saying A. So Regan, Parasurge, Alex, Tom, Sabi, Maddie, Anch, Bramble, Sinzoku. It's great to have so many people. Oh, it's A as A, says Joe. We've got Samaya. It's awesome to have so many new people in the chat. It's great to see so many names, people like Bramble, people like Joe, Regan, but it's good to have so many more people as well. Yeah, so basically the gradient is going to be equal to dv by dt, which is the acceleration, and the area is going to be equal to a half vt, which is equal to the displacement. So the answer is indeed A, not the rest. Okay, the diagram shows the directions and magnitudes of three forces acting on an object at a specific time as it moves through water. So it says the weight of the object is 1.2, so I'm just going to put a W by there. The upthrust is 0.8 and the drag is 0.6. Now, if the drag is going up, that must mean the velocity is in the opposite direction, so the velocity must be down. Now, looking at the forces as well, we've got 1.2 newtons down, and we've got 0.6 plus 0.8. So basically, if we think about it, there's going to be 1.2 down, and there's going to be 1.4 up, and that means the net force, or the resultant force, is going to be 0.2 newtons up. So, has it reached its terminal velocity? No, because the forces on it are not balanced. Is it accelerating? No, it's not getting quicker. Is it moving upwards? No, because it must be moving down if the drag is upwards, so it can't be that. Now, it's not accelerating, it's not getting quicker. In actual fact, it's decelerating, and that means it's going to be getting slower. So here, the answer is C. So imagine, for example, you had a stone, you dropped it into water. Initially, it's going quite quickly. It would slow down as it went into that water. Okay, we've got so many people saying C, 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 C. Yeah, so Head says C because it's decelerating because the resultant force is acting in the upwards direction. Somebody says that these multiple choice questions are easy compared to AQA. Oh yeah, by the way, for everybody out there, have you seen that I've done, and this is like a big important thing, is if you go to Physics and Maths Tutor and you go to the AQA section by topic, you'll see that what they've done is they've broken down AQA papers into questions by topic. You'll also see that they've got multiple choice questions by topic, and you'll also see within that there are work solutions to every single multiple choice question from AQA that I've written with Joe's help. Joe works with me at Physics Online, he's a physics graduate, and we basically put together this whole set of solutions, and I think there's about 700 multiple choice questions that I answered, so I've written out the full workings. So all of that is at Physics and Maths Tutor. Although it's AQA questions, it's going to be suitable for anybody doing A-levels to actually look at. Oh yeah, and that's, yeah. Okay, so next question. The object below is in equilibrium. A force not shown in the diagram also acts on the object. Which of the following shows the correct direction and magnitude of the force acting at point P? So there must be a force here. Now, I would say that, first of all, we've got a bit of a couple. So if we think about forces up and forces to the left and the right, well, basically there's no horizontal component of these forces, but there is a horizontal component of this force here, and therefore the force at P must have a horizontal component of force to the right, which is equal to that component of 5.6 newtons to the left. There's also going to be 10 newtons up and 10 newtons down, but there will be a component of this force upwards, just like there's a component to the left, and therefore there must be a component of that force down, and the resultant is going to be down to the right, like that. So I would say, as M, Anch, Bramble, Parasurge, Miss Katie Bell, Sinzoku, Bilbao, Maddie, Bilbo MC, sorry, Badger, Alex, Subi, WR Titan. Yeah, the answer must be B. There we go. So that one there, not too bad at all. Yes, I know the questions are relatively straightforward, but they're straightforward because I've been doing video lectures for you guys for the last few years. You've been taught well. Okay, this one's a bit more tricky. A particle X of mass m collides with a stationary particle y of mass 4m. Immediately after the collision, the particle x is moving at a velocity v1 at an angle of 60 degrees, and particle y is moving at an angle 90 degrees to that. So therefore, if that's 60, that must be equal to 30. So again, add stuff to your diagrams to kind of help explain that. Did Zed Physics do this today? Oh, wow. Well, he knows what I'm doing. He's just, yeah. Anyway, okay. What is the ratio of V1 over V2? So what I would say is that in the vertical direction, beforehand, the total vertical momentum was 0, because both of them, well, that one wasn't moving and that was moving to the right. Now, what we want to think about is in the vertical direction, the momentum of x upwards is going to be equal in size to the momentum of y downwards. Okay? So what we can therefore say is that in the upwards direction, there's going to be a vertical component of V1. Okay? And the vertical momentum is going to be, because we know that P is equal to mv, Px is going to be equal to the mass, which is m, times V1, and if that's 60 there, that's going to be sine 60. Yep. So that's the vertical upwards momentum, and that's going to be equal to the downwards momentum of particle y, which has a mass of 4m, and here the vertical component of velocity v2 is going to be equal to sine 30. Okay, now what you can see here is that there's an m on both sides, and therefore we can say that v1 sine 60 is equal to 4 times v2 times sine 30. Now we want to know v1 over v2, so v1 over v2, well, basically that's equal to, we've got 4 sine 30 divided by sine 60. Okay, now I probably should know these off the top of my head, but we've got 4 times sine 30. 4 times sine 30, I'm in degrees, well that's just a half, so that's 2, divided by sine 60 is equal to 2.31. So the answer is A. Right. All that for 1 mark. Yeah, people weren't as quick with the answers there, were they? And people didn't seem vapor as sure. Yeah, you said D, then A maybe, yeah. All of that for 1 mark. Okay, yes, you do all of that for 1 mark, but you will have seen that there's plenty of other easy ones that you could get in about 20 seconds. Power surge, you guessed A without calculations. Can this be done in the horizontal one too? Potentially, but I guess I'm sure you could do it horizontally, but I think this is probably, yeah. And I would say that something like this, though, is one you want to come back to at the end. So this one here, if you look at it and go, there's going to be some calculation involved. If you're not sure, this is the kind of thing that you maybe circle number 6. That means you know you've not done it, so you don't want to kind of leave your exam without at least guessing. But basically, this one here, I would say come back to at the end. Are the 2p equals? Yeah, so basically what we're saying is initially the vertical component of momentum is 0. So there's no momentum up or down. Afterwards, because momentum is conserved in both the x and y directions, the vertical component of momentum here must be equal to the vertical component of momentum down there. Okay, and that's because of the conservation of momentum. Okay, let's do another question. On to 7. So, a metal block of mass m is heated by an electric heater. A graph of temperature against time for this block is shown below. The power of the heater is P. The gradient is G. What is the correct expression for the specific heat capacity of the metal? Oh, this is good, right. So, what we know is that Q equals mc delta theta. Actually, this equation, it should be simple, shouldn't it? I wrote about this, I know it's too late if you're in year 13, but in my daily workout book 4, one of the first things I did in like my kind of first chapter is I looked at all of the equations used at GCSE for this equation to do a specific heat capacity. Q equals mc delta theta, AQA A-level physics, Q equals mc delta t is used by the same exam board in A-level chemistry, but they use E equals mc delta theta for GCSE physics, but basically it's the same thing, so we can use a Q or an E. A Q is quite nice, because the Q is basically our unit really, or our symbol to show its thermal energy. And these are available on Amazon. If you're in year 12, buy the book now. Book 4 starts at the start of July, and there's questions over the summer holidays into September and October, so the start of year 13. So year 12s, buy the book, you will not be disappointed. Yeah, okay. Right, okay. So Q equals MC delta theta. That means C is equal to Q over M delta theta. Now, is that right? Oh no, sorry. Let's do another step first of all. That's the energy transferred. Now the energy is equal to the power divided by time. And if we know that the energy transferred is equal to the power divided by time, oh no, sorry people, right, power is equal to the energy transferred per unit time. So that means if we want to know the power is equal to the energy transferred divided by time, which equals mc delta theta divided by t. Okay, does that make sense? So the power is equal to mc delta theta over t. And delta theta over t is equal to the gradient, which is delta theta over t. So delta theta over t is equal to Q. So we can also say that the power is equal to mcq. And if we rearrange this is probably not the neatest, we can say that C is equal to the power divided by the mass times Q. And looking across here, the one that's correct is going to be D. So here the answer is D. Okay, sorry about that. Yeah. Somebody says, any way I can buy the workbook so you get the full amount? I'm afraid not, Joe. If you buy the workbook, although it costs £9.99, I get less than £3 from it. But I think that's worth it for you to have a physical product. So there we go. Right. Why Q and not G? Is that all good? Yeah. Okay. Does that make sense? If not, pause the video there, maybe work through it. Okay, which statement below are implied by the assumption of the kinetic theory model of gases? So let's just go through these. We're going to ignore that first of all. A gas is mostly empty space. That is correct. Gas particles spend more time between collisions than time during collisions. That's correct as well. So the time of collisions is negligible compared to the time between collisions. There are always forces between the gas particles. No. We assume that there are no intermolecular forces between them. So we can say that 1 and 2 are correct. And I'm going to get rid of number 3. Okay, so which of these is that? That's going to be 1 and 2. So the answer for this is going to be A. Okay, is that all good? Yeah. So this one here, for 8, the answer is A. Right, Edward, do not worry about how many hours of revision other people are doing. It'll either make you feel really sad, or a lot of people are just lying. So do not care, or do not think about what other people are doing. Just do as many hours yourself as you possibly can without kind of burning yourself out. I think that's the most important thing. Okay, right, next question, number 9. Okay, so we've got about 6 more questions to go. I'll probably go on beyond 8:30 if you're happy with me doing that. So, okay, right, this one here. I would say that this question about gases initially looks a little bit confusing. So we need to think about which equation we can use. Now for that you will have your data sheet, and actually I guess the thing you need to maybe quote is that PV is equal to a third NMC RMS, that thing squared. So sometimes it's C bar squared. Okay, again, different exam boards even though it's still the same physics, they often have like slightly different symbols for this. Okay, and yes, N is going to be the number of molecules of that particular gas. Okay, now it says here we've got 1 mole, and that means the number of molecules is just going to be equal to the Avogadro number. And we want to find the volume. So the volume is going to be equal to the Avogadro's number times the mass of a gas particle times their RMS speed squared divided by 3 times the pressure. Okay, so we know all of those things because these are all given to us. So the volume is going to be equal to 6.02 times 10 to the 23 times the mass of a particle, so 4.7 times 10 to the minus 26 times 500 squared divided by 3 times 100 times 10 to the 3. So we've converted from 100 kilopascals into pascals. Okay, we do all of that. And this gives a number equal to 2.56 times 10, I did work it out earlier, times 10 to the minus 2, which is, in this case here, as some people have already said, like Holly, perfect, getting the right answer straight away, and Ariel, not quite yet. So the answer for this is C. So that one over there, and I think this is the thing where people often think there's a particular technique to multiple choice questions. In my experience as a teacher, students who know the physics really well, the A-star students who can kind of write a good written answer, they can do long calculations, they're also the students who tend to do better on multiple choice questions, because ultimately the more physics you know, the higher the chance you're going to get the right physics and just understand it to get the right answer. And I would say that this question here is one I'd leave to and come back at the end. Okay, right, so a mass is attached to the bottom of a spring which is fixed at its top end. So there's our mass. The mass is displaced vertically, then released. The mass oscillates with simple harmonic motion. When it's at its lowest point, so maybe this is the equilibrium position, what do we know about it? Well, the elastic potential energy at the lowest point, because it's extended down, is going to be at its maximum. So these ones here can't be correct. Now the gravitational potential at the lowest point is going to have its minimum value. So it can't be the maximum value. And the kinetic energy, if it's at the minimum point, that's before it oscillates back up. So it's going to have no kinetic energy because it's not moving. Hold on. Kinetic energy. Hold on. Is that right? Oh yeah, so it's going to have 0 kinetic energy. Ignore my crossed out there. And therefore that's correct, and that's correct. And the answer is B. Right, there we go. 9 is B. At the bottom is no kinetic energy. Yeah, my mistake on that. I think I would now, if I was going to be in your exam tomorrow, which luckily I'm not, probably Friday morning. Is it Friday morning that you've got your exam? I think it's going to be quite nice and sunny, so I might go and ride my bike. But if I wasn't riding my bike and I had to be doing exams instead, I'd probably start crossing through stuff in pencil, because if I make a mistake, I can easily just get rid of those mistakes. And obviously writing my answers in black pen so it scans in. Okay. Right. So, which pair of quantities do not have the same or equivalent units? So, for this, acceleration, just write down what we know. Acceleration is meters per second squared. Gravitational field strength can be newtons per kilogram, but that's also the same as meters per second squared. So they have the same units. The next one, angular frequency, is going to be in radians per second. Angular frequency maybe is in things per second, and a radian is basically a unitless thing, so these have the same units. Gravitational potential is going to be in joules per kilogram, and kinetic energy is going to be in joules. Now these do not have the same thing. Gravitational potential energy has the same units as kinetic energy, but gravitational potential doesn't. And I reckon, as Ahmed said, everybody reads this as gravitational potential energy. So yeah, impulse though has the units of Newton second, momentum, kilogram meters per second, and those two things are the same. So here, gravitational potential is not gravitational potential energy. So gravitational potential is joules per kilogram. Right, so the answer for that is C. That's tricky, wasn't it? Right, a few more questions. This one is nice. We've got 3 energy levels, X, Y, and Z, for an atom. Which transition is correct when the electron absorbs a photon with the shortest wavelength? So we know that E equals HF. The energy of that photon is equal to HF, or E is equal to HC over lambda. Now, if you've got something with a short wavelength, that means something's going to have a high amount of energy, because this is going to be really small, and that means this number is going to be really big. So we want to think about the biggest transition when the electron absorbs a photon with the shortest wavelength. So the electron is going to go up here, and we're going to have that biggest change between X and Z. So for this one, the answer is B. Is that right? Okay, people are saying different answers. Not X to Z, Z to X. Z to X. So the answer is A. It's A. Yes, I know. I just didn't read the answer properly. So always read the full question, and also, I guess, read the full answer when it comes to multiple choice things as well. Okay, light from a hydrogen source is incident normally on a diffraction grating. This question I would leave till the end, because basically I'd circle it, come back to it later. There's just too much to read. Now, for this particular question, this is useful if you are doing OCR. So this is not AQA. Okay, if you are doing AQA, then you might not be doing anything to do with astronomy unless you do your question 3 thing. So for this one here, this one here is not AQA, but OCR, do some astronomy stuff on paper 1. AQA is only the optional module in paper 3. So if you're AQA, don't worry about it. So what we know here is that we know that the speed over the speed of light is going to be equal to the change in wavelength over the original wavelength. Okay, now that's an equation given to you that you know for OCR. Okay, now we know that the speed of the star is 0.16 c, where c is the speed of light, and that means v over c is going to be equal to 0.16 c over c. So we can say that 0.16 multiplied by the wavelength, which is 486, is equal to our change in wavelength, which in this case would be 77.76. Now that means the final wavelength is going to be equal to the original plus the change in wavelength. So that's 486 plus 77 point that, which is 563.76. Okay, now we know that from a diffraction grating, is it diffraction grating? Yeah, from a diffraction grating, we know that n lambda is equal to d sine theta. And what we're going to look at is the first order, and we've also got the first order up there. So we know that n is equal to 1, and we're going to be using the same diffraction grating, which the light is going through. So we can therefore say that lambda is proportional to sine theta. Does that make sense? Yeah, this is the Doppler effect, the Doppler shift in this kind of redshift of that light. So we know that the wavelength is equal to sine theta, and therefore we can say that lambda 1 over lambda 2 is equal to sine theta 1 over sine theta 2, because we know that theta over sine theta is equal to a constant. So that's the thing we're going to use. We can then, of course, say that sine theta is equal to the new wavelength, which is 563.76, divided by the original wavelength, 486, multiplied by sine 30, which was the original angle. And if you do that, we find that theta 2 is equal to 35.5 degrees, which is the answer D, and the answer is D. Now that takes more than a minute. So I would say that this is the question that you do at the end of the paper when you know you've got enough time and you've put enough time into the longer wordy answers and the big calculations. So I would say that that's probably worth about 3 minutes worth of time to read the question, do the calculation and all that stuff. So I would say that's a lot of work for 1 mark, and therefore you've got to be ruthless. If you think it's going to take you too long to do, look at it and then just move on. Right. Okay. For this one here, number 14, we've got a galaxy. We've got the distance in light years away from the Earth, and it's got a recessional speed. Which expression is correct for the age of the universe in seconds? So for this, what we need to do is, I would say that we know that Hubble's constant h0 is equal to v over d. But of course, the age of the universe is equal to 1 over the Hubble constant. You know, a few assumptions made there. That's right, 1 over Hubble's constant. And therefore, that's going to be equal to d over v. Okay. Now, we need to have the value of d in meters, and we need to have the value of v in meters per second in order to get our value of our time in seconds. So the distance, well, it's 1.0 times 10 to the 9 light years away. And then we need to convert that into meters. And the conversion factor here is 9.5 times 10 to the 15. Now, you should probably just know that if you're at this point in year 13. If you can't remember, that's kind of data given to you in your data book. So that's converting from light years into meters. We then need to convert our recessional velocity, because it's 23,000 kilometers per second. But then we need to get that into meters per second by timing it times 10 to the 3. And so that's the value of the distance divided by the recessional velocity, which is going to be equal to the time. And that's going to be equal, I guess, to this one over here. So the answer is C, because that's the way that it's displayed. Okay, right, here we go. The last one is 1 mark. This is an easy one, because it's like basically something you know. Astronomers observe approximately the same number of distant galaxies per unit volume of space in all directions. What does that mean? Well, basically this means the universe is isotropic and also homogeneous or homogeneous. And that means it's the same in all directions, and this is the cosmological principle. So the answer for this is B. Okay, so this doesn't support the Big Bang necessarily, because it's a bit, I mean, it doesn't support these other things, but this idea supports the cosmological principle that the universe is the same in every direction. Okay, hopefully that helps a little bit. All right, so what are we saying in the comments? So OCR Physics have astrophysics on this spec. They do have particles, but that's in the other paper. Right. I reckon if you're watching this now, you're going to do all right, because you're kind of watching this stream, you're kind of engaged. I would say that for everybody out there, if you're not sure about anything, head over to alevelphysicsonline.com. There is stuff there. There's so many videos that explain every part of the course in loads of detail, and I can basically teach you everything from scratch if you're not sure about it. Of course, I do have a premium plan if you want to have extra videos for year 13, and you can buy that. It's just a one-off payment. There's no kind of discounts for the last few months. It's basically a one-off payment. Your schools can also subscribe if they haven't already done so. And if anybody out there would like to get papers, extra practice questions for paper 3, then you can buy those in my shop. And I think there's links there from the website as well. Apart from that, though, thank you, everybody. It's been great to have all of you here tonight. Somebody said, if you did all the AQA questions per topic for AQA, would that be enough to get an A? Yeah, I reckon so. You definitely get a lot of... I think basically, for all of you now, just do as many questions as you can. If you've done all the past papers twice already, you can definitely look at doing my practice papers that you can buy. You might not have done those yet, Bob. You can also do older specification past papers. You can do other past papers from different exam boards as well. So thank you so much. I will be back again tomorrow night and on Tuesday night, and on Wednesday night, and on Thursday night as well. So I'll be here every night. Thank you, everybody. And if you want to keep supporting what I'm doing, go and buy a premium plan. That's probably the best way to support me, so I can keep making videos. I'm going to move into a new studio in a couple of weeks' time, and it's going to be bigger, better, and so on. Yeah. So thank you, everybody thank you for everybody doing A level, and good luck for the GCSE kids doing English literature tomorrow. Thank you, and good night.